All right. So we're going to talk about graphs, some distribution, and their shapes. So, yeah, okay. Sorry. So the first thing is, what is frequency? So frequency is the measurement of the number of occurrences. So how many times something occurs? That's frequency, okay? So we're gonna talk about dot plots, and they just display the frequency of numbers. So what we're going to do is we're going to create a dot plot for the data below that is the age of maximum yearly growth for 35 boys. I don't know between what ages, it just gave us some numbers. Okay, so what we do is it just gave us like this giant list of numbers, right? So a dot plot is first made with a number line underneath. Ooh, that was nice and straight. Sorry. And then I find the lowest, and the lowest is 10. And then the highest is, it looks like 18. Yeah. So I just want to create a number line up to 18. All right, I didn't space those last out very well. Okay, good enough. So we just go through and we see how many times, like how many 10s are there? Well, I see 1, so I'm gonna put a little dot. And I go to the 11s and I see that there are 2. So I draw 2 dots above the 11. Sometimes you might see little X's. It doesn't really matter. You just need a symbol to show the quantity, the frequency of each number. And then I go to 12, and there should be 5. 1, 2, 3, 4, 5. Yep. So 1, 2, 3, 4, 5. And I didn't do the best at those 3. So, and with a line plot, you want to, or dot plot, sorry, try to keep the spacing even, so that way I can kind of see, you know, which bar is taller. Because if I smoosh all my dots together, then, you know, it's harder to see. So just to pick up the pace here for 13, there are, let's see, 1, 2, 3, 4, 5, 6, 7. For 14, there should be 9. And for 15, there are 6 of them. (16) there's 3. 17 and 18 each have 1. Okay, so the dot plot here, you know, it's not the fanciest graph, but it provides you a good display of how it starts out kind of low. It gets, you know, hits its peak here at 14, and then it goes down again, right? So we can kind of see that there's like a cluster that we could say, like, you know, probably the average is somewhere between 13 and 14, right? All right, so then there's another kind of graph called a histogram. So a histogram, it also shows the frequency, but shows the frequency of groupings of numbers. Whoa, I don't know what that was. Sorry. Okay. So what we're going to do is we're going to construct a histogram for the data that we just used of the height of the boys. So let me kind of scoot this up a little bit here. So a histogram kind of looks like a bar graph, but it's not. So bar graphs, just to remind you, represent like categories, and then how much stuff is in each category. It's like how many people have birthdays in January, right? And then you make a little bar. Histograms have to do with just numbers and the frequency of those numbers. So our setup here is we're gonna go from here. So a kind of a horizontal and vertical axis. And so we're going to do this in groups of kind of going by 2. So we're going to start here at 10. Next one is going to be 12, 14, 16, 18, and I actually do need to go to 20 here. Okay, so we would have, so each like chunk of that is called a bin, and so we have a bin width of 2. And then along here we're going to have our frequency. So let's go up to, let's see, we had the max of, well actually because we're combining stuff it's going to be high, so let's go by 2s here also, but we're going to start at 2. I think we can stop at 18. Okay, so over here, this is our frequency. These would be like the heights to label our graph here. Okay, so what makes histograms kind of difficult is, at least, all right, so there's kind of 2 kinds of histograms. There's a histogram like I'm doing, which I believe is the proper way to do it. Then there's histograms that you might see, and I'm going to erase this afterwards, where they give you bins and they just say that this is 10 to 11, and then they'll say that this bin right here that's 11 to 12 or whatever, right? 12 to 13, my bad. So yeah, that's fine, but I would like you guys to do histograms this way because I think it's the more proper way. So what we do is we're going to look at our bins here, and this bin right here, it's 10 up to 12. So it starts at 10 and then it's going to go up to like 11.999 whatever, right? So it always goes up to that number, but it doesn't touch that next number. So 12 belongs to the next one and 14 belongs to the one to the right. So you're always going to look to the right for it. So for 10 through 11, up to 12, but not including, we only have 3, right? So I'm going to go up 3 and show that. And then for 12 through 14, through 13, but not to 14, we have 12. So I draw, oops, that wasn't great, but so I draw my box there. 14 through 16, but not including 16, 14 through 15. There's 14. 16 up to 18, but not including it, there are 4. And then 18, yeah, it belongs in this one, and there's just one 18, right? So I go over there. Okay. So before I get to the next kind of question, I just want to talk about that, like, so the dot plot shows you very specific data, right? You've got every single thing accounted for. Whereas a histogram has kind of clumped stuff together. Like, we don't know that that is 18 versus 19, right? But when we're dealing with really large amounts of data, a histogram can show us trends a little bit easier to read than a dot plot, okay? And just to kind of think about, like, if we were to change the bin width, all right, if I was to change the bin width to like 3 or 4, what would happen to the bins? Like, what would happen to the height of the bars if you changed the bin width? So you should think that the height changes, right? So if you put more numbers into a chunk, you're gonna have a higher bar, right? And if you make a really small bin width, you're gonna have less numbers, less things in that. So the height of the bin goes up as the bin width goes up, and vice versa. All right, next page. Okay, so we're going to talk about what we call distribution. So distribution, if you think about just like, what does it mean to distribute something, right? It means like, how do you spread it out? And so that is what distribution means for us, is that how is it spread out? And so they came up with different names for different types of ways that graphs are spread. So if something is, sorry, let me go over the little document, the image first. So we could have a normal uniform distribution, meaning like everything's pretty much the same. There's no like super highs or lows, right? We could have a mound shape where it starts low, it gets higher, and then it comes back down again. That's also called kind of a U shape, a bell curve. We'll talk about that later. Then there's skew distribution, meaning that it's low on one side and high on the other. And then it doesn't go back down, right? It just stays that. So it could keep on going up. And it could go the other way, like it could start up and then go down. But either way, that's skewed. And then there's bimodal, right? We have different peaks and lows. All right, so there are 2 different types of skew distribution, which is what I have over to the right. So if something is skewed to the right, that means that the tail of the graph is to the right. So a quick little visual. That would be skewed to the right, right? It's trailing off to the right. And so skewed left's opposite. Okay. All right, so I need to refer to my pictures. Let me go back. So I've got this question down here. It says, what measure center do you think is best to represent each kind of distribution? So if we have a uniform or mound shape, or a normal curve, is also what it's called, or a bell curve, all those things, what do we think would be good to show the middle of this, where everything's either pretty uniform, or we have lows, highs, and then back to a low? So anytime we have something that's pretty symmetrical, is what I would call it, we want the mean to represent that, because the mean is going to give us really, it's going to take into account the lows and the highs, but really settle probably in the middle there as much as it can, because it's not being affected by anything too extreme, right? So when something's symmetrical, there's no extreme data on like one side or the other, and so the mean is a really good representation of that. So right here we're going to write mean, the average, right? But then if we have something skewed, so it goes off to the left or to the right, meaning we have some extremes, right? We have something really high and something really low. And when that happens, the mean is super affected by that. The mean gets pulled by the low lows and the really high highs. And so some people use that to advantage to kind of like skew the results and make it look different. But when we have anything that's too extreme, to really find the middle, we want the true middle. And so we want to use the median anytime we have anything too extreme and we have something skewed. Okay, because the middle is just truly you're counting in, right? As we learned about last time, you're finding like the actual middle number of all the numbers. And so it doesn't matter how high something is or how low it is, just one number is the actual middle of it. And so an example of this, just to kind of, I don't know, hopefully clarify this, if we have like, they often talk about the median price of homes versus the mean price of homes, because you're going to have some like $1 billion homes, right? Well, maybe not billion, but $1 million homes. And then you're going to have like, you know, your little tiny ones, right? And so measuring things through the mean, those super expensive homes would totally pull your mean in the wrong direction. And so kind of here's a graph here. So let's, I don't remember what this data actually is, but we'll just pretend it's maybe kind of flipped. And so like, if you have some really high home values here, what it does is it's going to pull the mean. When you have some really low lows. So, well, okay, I'm going to go ignore the graph for a second. I'm going to go back to talking about my house costs. So you're not going to have very many homes that are millions and millions of dollars, but just because of how expensive they are, they're going to pull, quote unquote, the average cost of a home to be higher than it really is, right? Like most people don't own a home that expensive. So that's why they look at the median to be a better representation of what people actually own, because the median is truly the middle of, they take like all the home values in the area and they literally find which one is in the middle. And that's a better representation because it's not being pulled by the super rich houses to be higher than it really is. So it's a better representation of the actual population. So this one down here, I really wish that I knew what this was representing. But this graph kind of shows you've got a lot of high highs here, but you've got like this tail out here, right? You've got this skewed to the right is what we would say. And all of these out here are making that mean pull over, right? It's a little bit to the right. Whereas the median, where really, this is truly most of the data over here, is showing the median. So like back to my home thing, it would kind of be the opposite, right? So if we had like over here, this is like my $5 million homes, right? You maybe have like one in an area, right? But you're going to have tons of home values over here, right? And so, I guess so this graph does work for this. So we want the median to show that really there's a bunch of homes that are at these lower costs and very few that are at the higher. Okay, I think I've rambled enough on that. Let's go to the next page. Okay, so we've got some dot plots here. And this is a random sample of 80 viewers of a television show was selected. And the dot plot shows the distribution of ages in years of these 80 viewers. So, kind of look at the dot plot and what we got going on. All right, so then the first question is, so what do you think this graph is telling us about the age of the 80 viewers in this sample? So what do you guys, what would you think about the ages of people watching? Well, we could say like not many young people are watching it, or nobody, in their 30s, except for late 30s, are watching it. So really there's a large population between, and that's, 60s to, above 70s range. So we say that it's kind of an older population. There's a lot of people between, 61 to 75, 73. Question number 2, based on your work dot plots, whatever. How would you describe this dot plot as representing symmetric, skewed data? So the stuff that we just talked about. Which way is it skewed? And we would say that it's definitely not uniform. It's not symmetric, right? And it's not really doing a mound curve or, a bell shape of any kind. So we would say that it's skewed. But what direction is it skewed? It's skewed left, hopefully, is what you were thinking, okay? Because we have the tail here and then it's getting more up there. And so we always go to the lower side, so it's skewed left. Okay. All right, next chunk. A random sample of students from Wilsonville and Westland were surveyed, and by the way, this is made up, about how many pets they own. The 2 dot plots show the distribution of the number of pets. So we've got the Wilsonville student stuff, then we've got some Westland. So what do you think these graphs are telling us about the number of pets students have? Well, we could say that, the Wilsonville students seem to have a bit of a more range of stuff, right? Some have hardly any, some have a lot, whereas the Westland students are kind of grouped towards, not as many pets, right? But a lot with 2 for some reason. So any of those things works. We could say Wilsonville has a wider range. And Westland is grouped more. All right, and then talking about the shape, our distribution of them. So for the Wilsonville, we've got some highs and some lows, right? And it kind of goes up and then it goes down again and then it goes up again. So we would say that the Wilsonville one would be bimodal. And then for Westland, well, kind of look at the shape of it. Right? It's not perfectly symmetrical. That's pretty good though. So we'd say that's mound shaped. Okay. All right, last thing, interpreting a histogram here. So we've got the following histogram represents the age distribution of the population of Kenya in 2010. And this is actually somewhat legit data, if I remember correctly. So what do we think this graph is telling us about the population of Kenya? Well, we said there's a really young population, right? There's not very many people who are making it to an older age. It's a very young population. Gosh, I'm struggling. All right, very young population. There we go. All right, and based on your previous work, blah, blah, blah. So how is it distributed? Is it symmetrical? Is it skewed? So we would say that it's skewed right. Okay. All right, and last question, what measure of center would be the best? Anytime we have skewed data, we always want the median. Yeah, okay. All right, sweet. So your assignment is posted on Google Classroom, and yeah, have fun.